Hi everyone, I'm Deep Nayak. I work as an applied scientist in the international machine learning team at Amazon. In this module, we'll be covering details about agentic frameworks, specifically how agents work on top of the LLM architectures that we all are very well versed with, and what are the different modes of operations that agents work in, and how we can use it in different scenarios. So, first, quickly starting with a core concept that forms the entire agentic framework. The idea is that an LLM usually is a one is to one mode of operation where we ask it a question and it will keep answering it in a token by token manner, right? But it does not understand whether it has completed the job or not. We have to basically give it feedback and then wait for another turn to like get its response and then identify if it worked correctly or not. This probably works well in an open-ended scenario where we are asking it to generate some text that we want to like creatively generate. But in a scenario where we have deterministic tasks, where we already know that we want to, let's say, modify a code file in this particular place, or let's say we want to modify a button's color in a particular web page. We already know what the end goal is, right? We already know that it can be verified, it can also be quantified, and we can say whether it's complete or not. Um, if we just wait for the model to get back with a response and basically just edit one file at a time and then look at the response, look at the changes made in the file, and then kind of give feedback back, it will take a lot of time and effort, which can actually be automated in some form, right? So that's where agentic systems come into the picture. They basically introduce a loop in the entire workflow where once an output is generated by the model, it is fed back to the model itself to kind of validate if it makes sense or not, and then decide how it should proceed next, right? So this closed looping of the entire model calling is what agentic systems are all about, right? So now quickly coming to like the formal definition of what an agent actually means. So as I mentioned, the idea with an agent is to basically create a loop, right? So, for example, you have an LLM which acts like the brain of the entire operation. The LLM's task is to basically identify what are the steps in completing a particular task and what are the different things that it should be doing, right? Once it has noted all of these down, it will basically have access to tools that are present in the environment. So, you can think of tools as functions that are present in any code system, right? Basically, they have very specialized use cases that they execute. For example, one particular tool can be search, where all the tool does is basically given a key phrase, it will basically search it on the internet, probably through Google or through um, binge, and then come out with some output, right? So that's all the tool will do. It has a very specialized use case and it will just focus on completing that task. Now, what an agentic system will do is that it will know what is the description of this tool, what are the capabilities of the tool, and it will give that to the LLM. So the prompt will basically contain a setup where you are telling it this is the task and these are all the tools that you have at hand, and you'll have a description of this search tool in that prompt itself, right? So now the model knows what is the task and what are the different tools that are available to it to actually execute that particular task. And if it identifies that, okay, I probably need to search something on the internet, it will know that there is a search tool that's present. And what it will give us in return is basically some parameters, some key phrases that we want to pass to this search tool, right? Now, what will then happen is as part of that loop, we will make sure that the tool is actually executed. We actually call that function or that tool and perform that search that was requested by the LLM, right? And whatever output we get from that tool is then fed back to the LLM to kind of reconsider, right? So let's say it was searching for green parks in Mumbai. It will then basically look at the results from the search API, and then it will go through each and every result that came up in the search query, right? And then it will again kind of think about whether it matches the query, which was green parks in Mumbai, and whether there are any false positives in there, right? And if it thinks that it has correctly identified the end goal, it will stop right there, or that should be a capability that agentic systems should have which is basically to understand when to stop. But otherwise, it will go back to another tool where, let's say, you want to look up in a particular database and then come back with some result and give it back to the LLM, right? So this entire loop system is what we call an agentic system, and it kind of dictates how automated systems work with respect to LLMs, right? Now, there are multiple types of agentic systems that we already interact on a day-to-day basis. So one very basic agentic system that we are familiar with is the chatbot, where we are driving every turn, right? So where we are kind of interacting with the output that the model is giving to us, and then going back to the model with some more questions. So we are the ones who are closing that loop. When you think about another layer on top of these models, it's basically a co-pilot like setup, right? Where essentially the model is giving some output and it already knows where it should implement and what should be the next step, but it is first asking you to approve that particular change, and only then it will kind of execute it, right? And then there is like a fully automated agentic system where all you have to do is give it a single prompt, and it is then the owner of actually identifying what to change, writing that change, and also verifying that change. Um, which is what we see nowadays in systems like Claude Code and Kiro for that matter, right? So these are the different types of agentic systems that already exist in the real world, and we have been interacting with them. But this is one way to classify different agentic systems, right? Now, there is kind of like an autonomy ladder that exists whenever you are working with such agentic systems, right? What I mean by that is you basically decide how much control you want to give back to the model at every step. So, in the first stage where I was talking about, let's say, Copilot, right? You are reserving the control over what kind of changes the model can make to your code. Unless you approve, that change will not be implemented. But in the case of Cloud Code, for example, even Cloud Code actually asks for what changes you want to make, but it has a mode of operation called auto, where you can actually give it the control to modify or decide which changes to implement in your code files as well, right? So that is what the autonomy ladder kind of represents. So it also helps us decide when we should rely on agentic systems and when we should not, right? So for example, if you just have some task that requires a single tool call, right? For example, if you want to search for something on Google and you want to find or go through the results as it is in their raw form, there's no need of giving this task to an agentic system, because it will kind of overcomplicate the entire setup, where it will first ask the LLM to come up with a plan and then kind of execute that plan, get the results, and then format it and show it back to you. So there you don't actually need the use of an agentic system. But as soon as you introduce any more complexity, for example, you want to filter out the results that you're getting from that Google search and then perform some actions on top of it, you would probably look at agentic systems, because you want that process to be automated and kind of handle the nuances at different steps in that entire process, right? So there is one caveat that actually happens when we are working with agentic systems. It is that we usually run into scenarios where agents fail very quickly, and we are not able to detect these cases very early on, right? So, for example, if you give an agent a very complex task, let's say you want to add a completely new component in a web application that you are building. And you just ask an agentic system to keep executing, and it does not need to come back to you for any kind of tool approval. What will happen is, if it goes wrong in any one of these stages when it is creating that component, and if you're not able to identify that early on, you will end up in a scenario where all the other steps beyond that mistaken step will be kind of poisoned, right? So and it will reach a stage where you have a very low rate of success, because there are a lot of moving parts and a lot of components that you were actually not aware about. You were not intervening in those scenarios, and at the same time the model was not verifying the output at these stages, right? So without the right guardrails, it is very easy for agentic systems to kind of fail very immediately, right? Some very simple modes of failure are listed around here. So for example, there is a possibility of an infinite loop, where basically you give an agentic system some task, and it will keep repeating or keep going in a validation loop, where it comes with some output. It thinks it does not have the final answer yet, and it will repeat the same task again and again. And without any validation or gating system in place, you'll end up burning earning a lot of credits or a lot of money at the same time, right? There is also this concept of hallucinated action where it will assume that some tool exists, and in reality that tool or that function actually does not exist. So it will end up failing at that stage, and it will end up hallucinating some answer that acts as the output of that tool that never existed, and then continue the entire pipeline execution, right? So all the other steps that it executes beyond that part kind of is a waste of time and energy. And at the same time, as I was explaining, the cost can actually go up very, very easily. So this is just one interactive graph that I had in place where we are saying there is like a per step confidence that we want to have in place. And as you reduce that per step like success rate, the overall success rate also goes down dramatically. And as you increase the number of steps, that's actually going down exponentially, right? So for a case where the per step success rate is around 86% and the number of steps is around 40, the chances of end-to-end success actually come down to only 0.18%, right? Which is a very, very low number. So without the proper gating and the proper validation steps, relying on agentic systems is very, very hard because the errors compound very easily, right? So um, now coming to the question that we were answering a while back as well, right? When should we actually use an agent? As I had mentioned earlier, it actually depends on the type of query that you are working with. So if you have a very simple query, like I was mentioning, where you just want to search on Google and look at all the results, you probably just need to do an LLM call, or for that matter, execute that search query yourself. But at the same time, if you have a complex query for that matter, where you have some flight that may be rescheduled, and you want to do something with the insurance for that particular flight, right? Then there are a lot of moving components involved, and maybe a lot of steps that you can get automated through an agentic workflow, right? One thing to note in this entire process is that whenever you are working with a task where the path is unknown and dynamic and can be decided on the go, that's where you should rely on agentic systems to kind of get to some single answer, or like an accurate answer, right? And at the same time, whenever you're using agentic systems, if you identify that an action is irreversible, for example, you are asking an agentic system to manage your flights for you, and one of the steps involved in that managing part is actually canceling some of your flights, which cannot be reversed very easily without cost, you should always gate it behind a human, right? So this autonomy actually comes with a cost, as I mentioned here. And if you are not verifying all of these risky steps from a human, it will be very difficult to recover from such actions, right? So whenever you are working with complex queries, make sure that if the path is dynamic, you're relying on agentic systems, and at the same time you have the right human validation steps in between, right? Now, there are multiple ways to build an agent. Basically, once you have an access to some LLM, how do you kind of build on top of that to create an agentic system that works in an automated manner, right? So, as I was mentioning, there are two components to any agentic system. One is execution, and the other is thinking, right? But there is another component that's equally important with these two, which is basically observation. So, the idea is that you first start with a thought. You first ask the LLM to come up with a thought, and once it has understood what it wants to do, then you should ask it to come up with one particular action, right? This entire framework is called the React framework, where it first thinks and then comes up with an action. And the third thing that actually completes the loop is observation. So once it has some output, it should then go back and think about what it has so far, right? This was the chain of thought that it had created. This was the output that it got till this stage. Now, what is the next step that it should do beyond this? This process actually makes the entire thing grounded. So, for example, if you're only working with a scenario where you're not allowing the LLM to perform actions or make any tool calls, but only keep thinking, you will result in a scenario where a lot of the steps are hallucinated, right? And you are not able to get to a answer that's actually grounded. At the same time, if you're only focusing on actions where you're asking the LLM to just keep executing as much as possible, you will end up with a scenario where it is not reasoning about what it has found or what it should do next, right? And it will just keep calling tools randomly without any grounding. So this entire framework is called the React framework, where it will first reason along the way, and whenever it is acting, it will get the output and again reason if it makes sense to conclude the observation here or move on to the next step, right? The other framework that's very prominent nowadays is called reflection. So the idea here is that without training the underlying LLM, you want to get to a scenario where it is learning from its mistakes, right? A very crude way to do that is basically, once you have given it a task and let's say it has failed at any point in time, you would actually ask it to think retrospectively and understand where it failed and why it failed, right? And the LLM itself will have some learning by inspecting the entire tool calling or the entire chain of events that it has executed in the past. Once it has this learning, you can actually save it in some memory bank. And then whenever it is executing again, you can add that memory back to the context so that the model or the underlying LLM is aware that it should avoid these mistakes that it has made, right? So in this process, if you think about it, you are not touching the model weights at all. The only change that you are making is making sure that you are recording whatever mistakes you are making along the way, so that the model can learn and redirect whenever it is executing again and not make the same mistake again, right? This kind of a system is called reflection, where it's learning from its mistake without any kind of underlying training. And if you see this diagram over here, you'll see that the number of like the percentage of tasks that it solves with this reflection framework actually goes up very nicely, right? As you increase the number of trials, the success rate is actually higher very quickly, as opposed to a case where you will basically stall to a particular point if it's not learning from its own mistakes, right? Um, so this is again like a form of RL that exists when you are working with agentic systems. Only one thing to note here is that you will essentially incur some cost associated to every step that you have in this particular procedure. So for every attempt that you're making and every memory that you're saving, you're incurring some cost for every retry, right? So the more accurate your memory bank is, the more accurate your final output, and the less number of retries you'll need to get to the final conclusion also, right? um, Now, one more architecture or mode of operation that's very, very prominent is basically plan and execute. So there's a very prominent framework by Amazon that's called spec-driven development, where you first identify what are the different components that you want to change, and even before that, what are the different changes you are envisioning for the entire task, right? Once you know what is the overall high-level helicopter view of the total final changes that you are looking for, then you can ask the LLM to actually narrow down on what are the tools it should call, or what are the components it should touch. And then once it is sure about the entire plan and knows that every step is deterministic, only then it should proceed to execution or tool calling, right? When such changes are made, we see very high gains in the accuracy of the final output. It's just that we kind of invest some amount of the original or initial cost to making the plan as robust as possible, right? The executor here can be actually a cheap model which will just take in instructions and execute. And whenever it has some findings, it will just go back to the bigger model, stronger model, which has actually come up with a plan, right? And it will reorient that plan if something goes wrong, right? So there was an interesting study with respect to this as well, when a task was given where you had to rearrange some blocks, and there were some actions that LLMs had access to, for example, pick up, stack, and um, like which blocks you want to apply that operation on. The Like this was the performance as you see across different models, right? And when you actually obfuscate the tool names themselves, when the model does not know what a particular tool does, it will actually drop its performance right down to zero, right? But you see that there are models like O1 Preview which are actually able to still retain some amount of success rate. The reason behind that is they are working in a plan and execute setup. So they are first reasoning what are the different steps that they should take before actually executing them um, in the final setup, right? So this is just one way of making sure that your agentic system is more robust and works in a deterministic manner and has lesser chances of failure, right? Now so far we have covered like the react mode of operation, the reflection mode of operation, and also the plan and execute mode, right? And each of these things actually have like different caveats or different costs associated to them. So, for example, if it's a very long task, it makes sense to actually first plan it out and then execute it. If you know that a failure is very costly and it can actually give you a lot of insights, you can actually rely on reflection, or you can use a combination of all of these tools to kind of reach to your final state, right? Um, but if you have a liberty to kind of explore different paths to get to a final answer or to a final state, and let's say that state itself is not very deterministic, then you can probably rely on techniques like tree of thought, right, which we'll cover next. So the idea with tree of thoughts is basically that if you take like a very simple example of like some new numbers, and like if you want to find a way to reach the number 24 through some arithmetic combination of these numbers, then the model has like many different options available, right? The answer is not very deterministic. There are different ways to reach the final answer. And at every stage, you want to kind of verify what's the total you are getting to and if the next step is possible or not. So for such a setup, what makes sense is like a chain of thought process where it will first try to lay down different steps that it wants to do and then come to the final conclusion. But if you rely on a single chain of thought, there's a high failure rate that you can encounter, right? Because if it goes wrong at any particular step in that chain of thought, it will not be able to backtrack and correct that. So what we instead do is basically this tree of thought setup where you first start with like the original numbers, and then you have multiple options available for the first step itself. And then you actually trace an entire branch from each and every option, right? So, for example, in this setup, 6 minus 4 is equal to 2 actually is correct. And the same is true for 4 plus 8 as well. But this 4 into 6 does not make sense because let's say we are not allowed to use multiplication, right? So, and let's say we are not even using the other numbers in that setup. So we'll just terminate that chain of thought there itself because we know it is incorrect and there's no point in going further. But if we think there is a valid candidate, then we can actually proceed with the next step, right? So now that we know we have exhausted 6 and 4, we will then rely on the other numbers to come with some output. And then we identify that, oh, that's not a valid combination and we won't be able to come to a final answer. So that's where we'll actually backtrack, right? Similarly, if you are in a branch where you're getting the right answer, you will keep proceeding and generate the final answer. And you'll keep evaluating at every stage, right? So the benefit of this approach is that since you are exploring multiple options at every point in time, you are able to get to the right answer a lot more times as compared to a single chain of thought setup, right? Even if you're working with a setup where you are just sampling multiple um, chain of thoughts and then picking the best answer from it, this tree of thought actually has higher success rate as compared to that best of 100 or best of X chain of thought process as well, right? The only problem with this process is basically the token budget, right? So with basically a lower token budget, we see that there's a stark difference between tree of thought and chain of thought. But as the token budget increases, the chain of thought and tree of thought gap actually decreases, right? So this is just one option that's available, one more option that's available in agentic systems when we are working with these setups, right? So now let's look at how an agent decides, right? So we want to basically understand when an agent decides it should invest more on thinking and when it should invest more on like action, right? So these are some things that we can add as guardrails to our agentic system itself. So whenever we encounter, or whenever the agent actually encounters a scenario where the action is very easily reversible, for example, it's like reading a file, right? If it's not sure which file it should read, but it has some candidates, it's actually better to just read those candidates and get an answer, right? Instead of pondering or thinking whether it should select one file or the other file, right? So in this scenario, the cost of selecting an incorrect option is actually very less, and that in fact motivates us to actually execute more as compared to thinking more, right? But at the same time, there are scenarios like emailing all customers, right, which are a bit challenging because you have a very like a decently high cost associated to that wrong action. If you're sending out a wrong email, if you do it multiple times, you'll end up losing customer trust. On the other hand, if you have some actions that are irreversible, for example, dropping a database, then it makes more sense to invest a lot more time thinking what the agent is doing, right? So the agent should be super sure about what it has thought about and what it is actually executing, and maybe also implement some human feedback in the loop to ensure that it is not taking the wrong step before actually executing that, since it is irreversible in nature, right? So um, this is like one type of operation that the agent should be able to do on its own. It should understand the cost of an incorrect action, and such information should actually be present in the task description that you are giving an agent. And the agent should also be well equipped to actually take that task description and take that cost into account whenever it's deciding the next steps, right? Um Another way of looking at this is basically looking at the cost of asking for human feedback, right? So if you are looked at the recent advancements in like these automated coding tools, for example, even Kiro and Cloud Code, there are steps when you are working with these tools where they ask for your feedback before actually taking a decision and executing on that decision, right? So the idea here is, again, we need a way to identify when the model should ask the end user and when the model should just execute and show the end result to the end user. And this depends on the confidence that the model has on a particular step. So for example, let's say we have a way to quantify the confidence, probably through some classifier for any particular given step that an LLM has in their pipeline. Um, we can define a threshold on top of this confidence, right? So we can say that if the confidence is less than 50%, we should actually go back to the human and ask for feedback from the human instead of actually just acting it. But if the confidence is very high, if the confidence is more than 50%, then it probably makes sense to just execute or act on the action items that have been identified and then show the final result to the end user. So in this simulation, you can actually see that there is a cost associated to human interruptions. If you're interrupting the human a lot of times, if your threshold is very high, your cost will also actually be very high, right? So you are making 18 human interruptions and your cost ends up being 18 in that case. And you are always asking the human, so you will never have any incorrect action. But now, if you reduce this threshold down to like a more lower threshold, for example, if you have a threshold of let's say zero point 0.7, you will still have no wrong actions because most of your actions that have been identified are high confidence and have a very low chance of failure. And you'll have a lower cost as well because you're not interrupting the human so many times. But there's a sweet spot where basically if you go beyond that threshold, the cost of making an incorrect action is 10 times more than the actual action itself, right? So the cost actually then goes back up to 33 and like higher values. So there's a sweet spot that exists at let's say 0.43 where you have the total cost as 6, where you are asking the right questions to the human and just executing on the fly for highly confident actions, right? So such a setup is actually very crucial whenever you are working with agentic systems. You should ideally have a test set or a framework where you're evaluating these confidence against different threshold values and then deciding how to proceed. Yeah. There is also another setup in these agentic systems, which is called validate, retry, and escalate. So the idea here is that whenever the LLM knows or understands that something is not working out, it will naturally try to attempt and retry that task with a different action, right? Even if you have that reflection setup in place where it knows what went wrong, there is always something that the LLM can try, and there is a form of optimism that the LLM works with, and it will keep retrying until it reaches the final goal. So um, what happens in this scenario is that it will end up in an infinite loop, and it will keep retrying with things that actually don't make sense. Whereas in that scenario, it would ideally make sense to escalate it to the human who is actually interacting with that agentic system and ask for an alternate option, right? So a very basic thing that can be done in these setups is to basically set up unit tests. So there can be some sanity checks that can be in place, which can tell if an action is even correctable or not, or if something can be achieved or not, right? So that unit test can actually select the winner. Uh, and basically inform the model whether retries are meaningful enough or not. If this unit test does not exist, it will basically keep retrying infinitely and not go back to the human and ask for the next step, right? So this is one more thing to keep in mind when you're working with an agentic or building an agentic system, that it should have this guardrail in place so that it can kind of decide on the go. So, in conclusion, so far, what we have learned is agentic systems have this underlying phenomena of closing the loop with LLMs, where they are able to feed back the output that they get from different tool calls and decide what should be the next step, right? As we have discussed countless times in this session, these four things, these things that create the loop actually are not enough to make sure that we have a robust agentic system. We need to have these guardrails in place, which is basically choosing the right architecture, understanding when to think, or when to ask, and when to retry, understanding what to store in memory, and also understanding what are the different guardrails that the agentic system should have in place. So unless these four pillars are in place in an agentic system, we won't have a very robust or correct output from such agentic systems, and we can run into issues where they keep executing in a loop, or do not get back to us with like the right output. So um, that's like a summary of the different types of guardrails or different types of modes of operations that we have with agentic systems. In the next or upcoming modules, we'll actually learn how different agentic systems talk to each other and interact with each other to come up with a final output, which are essentially called like multi-agent systems. Thank you.